All right. So I know this is the last stretch for people, and I'm going to try and keep this short because I'm sure you guys could use a break. And besides, a lot of these things are online, so if you're interested, you can always look them up. So I wanted to cover a few things. I'll still do a little bit of hands-on things over here. So hopefully you can all log into your SSH sessions, and we'll see if it works. I haven't tested this on the cluster, so we'll find out. It's live demo, and sometimes they say you get demotitis. It's a new disorder when you do live demos. But we've been doing a lot of live demos. It's just that we had tested some of these things a little bit. But what we're going to do is look at a couple of things that helps you create environments that are consistent. So one of them is this project called Neurodocker, which a person in my group has been developing. It allows you to generate these Docker images with simpler instructions. So since you guys are not very familiar with Docker, what Docker entails is creating a file called a Docker file and building from that file. Now what a Docker file looks like, I'll pull up a few examples over here. In fact, let's pull up the one that we were using. Docker file. Okay. So I will post the link onto the Scratchpad so that you can, in case this doesn't come up very well, you can see it a little better. It is a set of commands that you give Docker and say, this is how you build this environment. So I don't know how, I mean, most people here, many of them, you are using Windows and OS X. Right? There's one Linux computer over there. So besides him, most of you are using an operating system that was already pre-configured for your needs for most things. And if you needed a package, you went to some website, you downloaded it, and you installed it, and you ran with it. So when you used DSI Studio, you went to dsistudio.labsolver.org, downloaded it, it was an executable graphical interface that you use. For many things where you end up doing the kind of scripting that you're doing, you're creating environments. So we saw an example of, what's his name? Amin? Who just spoke?
Yes,
I'm using Spider, which is a Python IDE, which installs various packages. So it required a Python environment inside his machine. So you can use Miniconda to deliver that Python environment. You can use other sources. When it comes to a lot of the imaging things, FSL, FreeSurfer, various other diffusion packages like MRTrix, you need to install them into Linux environments typically. And what Docker allows is to encapsulate those things into a consistent environment. But creating these things does require a fair bit of work. There's a lot of knowledge that goes into ensuring that this Docker container has the right set of configuration to install these tools. What Neurodocker does is obviates the need for this. So let's go to the Neurodocker example. So Neurodocker itself is a Docker image. So just like you've been running Docker images, we can run Neurodocker as a Docker image. So it's already pre-configured like a command line binary. So you could run that Docker image and say --help, and it'll give you help for how to use Neurodocker. Let's take a look at the supported software for Neurodocker. So it currently supports a couple of versions of AFNI. It supports a few versions of ANS. It supports any version of FreeSurfer that has binaries available. It supports any version of FSL that has binaries available. It supports Python environments, so it will use Miniconda to create Python environments for you. And within those environments, you can use Conda or pip to install various packages. It supports MRTrix, supports Neurodebian. So Neurodebian so you can't use Neurodebian on any arbitrary OS, but if you do have a Debian or Ubuntu OS, then anything that Neurodebian supports in the imaging world becomes available through the command line over here. And finally, for those people using SPM, it supports version 12 of SPM without requiring a MATLAB license. So all of this is available. So let's take a look at an example. A very simple example. So this first line over here will generate a Docker file that's based on Ubuntu, release 17.04, and will install ANS version 2.2.0 into it. Now, ANS might be unknown to many people, but it's a set of imaging tools that are used in neuroimaging quite extensively. And then, if you pipe this to the Docker build command, it will build that image for you. So that from that point on, you can use that Docker image, which has ANS installed. If you wanted to do something a little more complex, here is one. It's complex enough that it doesn't fit on an entire screen, but we can walk through this. It says that our base image is Debian Stretch, and then it uses the package manager in that operating system to install Git and Vim. It'll install the latest version of AFNI, ANS 2.0, FreeSurfer 6.0. This min equal to true is a special flag for FreeSurfer, which is targeted for recon all. FreeSurfer does a lot of things, but if you're only interested in doing recon all, it installs a minimized version of FreeSurfer. We can talk a little bit more about minimization, but just to give an example, if you download FreeSurfer and install it on any machine, it'll take up about 10 gigabytes of space. This minimal version is 800 megabytes of space. So space may or may not be an issue in certain circumstances, but this actually just limits it to what you need for. Then it installs version 5.10 of FSL. Then it switches to creating a user named Neuro. This is how you've been using this thing. We could call this user anything, ABC. It would become ABC. And then it installs in user space your Python environment. So in this particular case, they're installing NumPy, Pandas, and Reprozip, and traits, and Nipype into this Python environment. Then it adds a second Python environment and tells Neurodocker, Neurodocker says, I'm not going to make this the default environment. So Python environments can clash with each other. If they're both in the path, then whatever is first in the path will take precedence. You can switch user back to root and install other packages. And you can set up environment variables and other things. So it becomes a way of creating a Docker file where some tool under the hood is taking care of all the configuration needs for these tools. If you had to generate this Docker file, and we can try to do so by copying this command, if I can. Going to the terminal, coming out, and saying Docker file. It generated a Docker file. We can take a look at this Docker file. And as you can see, every single instruction is there. Now, if you were to install this, you would have to determine that each software package has these dependencies that you need to install. That's a lot of knowledge that's packed into a simple tool where all we did was create the specification to generate the Docker image. Well, we haven't generated the Docker image, we've just generated the Docker file. But yes, let's see how many lines of code did it generate? So you can use the WC command, 222 lines of code. You would have had to write those 222 lines of Docker configuration. More importantly, it's not so much the lines of configuration, it's the knowledge required to write those lines of configuration. You would have to study every single package that's out there, how it's installed into that environment, and do it. So this is an open project where people can contribute how to install different packages into various environments. Our target, at least in the slightly longer term, is going to be that we can build these packages from source, so compile from source. So as an example, Google compiles every single piece of software they use from source down to the kernel when they do their testing. That's the level of testing that they do for their software when things break. We don't come anywhere close to that in the scientific world. We hardly even test software. So these are all kind of steps towards being able to do something like that and make what we use as solid as possible. I kind of give the example that I used to say building tools is like designing cars, but in the world of science, it's really like designing the Mars rover. You're launching into unexpected terrains. You don't know how the tool is going to react as the shifting environment is changing. And these tools that we're looking at allow us to create and expand and change tools as we run into issues. So this is how we generated the Docker images that you're using as a quick exercise that everybody can run. We can do the following, which is we can, instead of generating a really large Docker file, we can actually try and generate something. So there are very few people who've used Unix systems here before. Let me ask those who have used it, is there a favorite command or package that you like? Because these base images come with very minimal things.
Ubuntu 16.
Ubuntu 16, okay, I got one. So, can you help Eric build an Ubuntu 16?
Alpine?
You want Alpine, okay? He's going to help us build Alpine, which is different. So we're talking about different flavors of Unix operating systems. And do you want something in that?
Oh yes. Piece of FSL and.
Okay, so that might take a little time to build, but we can build the Docker file pretty quickly. So the first thing we will do is we'll type in this thing. So that's your generation command. And as we talked about earlier, if you wanted to get help, you would just type help. And it will tell you we do a few things in Neurodocker, generate things, trace things, merge things. So we'll talk about reprozip, trace, and merge in a second.
Does this have the option to include new tools, one-line tools, which are not quite out there, they're no Nipype? Because part of bringing in some of the new tools, we get to create the nodes in the Nipype interface for them, but also to actually install them.
Right. So it can, with some of the newer tools, you need to know how to install them. What it can do is we do have latest versions of some of the tools available. But if you are looking at a tool that's not included in the standard list, you can then add it. So we can take an example over here. So we generate, and you said you want the base image to be Ubuntu 16.
I think it's Ubuntu Trusty. Oh no, it's in XE. The Y is a U after.
And then you wanted,
let's just add ants. Okay, just for the demo.
anything else? Well, this is not Alpine, because that's a base OS image.
Nylon.
So nylon would require conda. You have to specify which Python version you want. You can go with 3.6. And you could say conda install nylon. Okay, it's a very straightforward system. Yes.
Can you tell me which link is it in NDView? The link in NDView?
Yeah, it's the last one. So we'll paste it. It's not there. There you go. Oh, not that one. Pasted it wrong. So we can simply do this, and if I don't ask it to write it out to a file, it will just write it out onto the shell. So we can take a look at what it did. It said, use Ubuntu Xenial, installed some dependencies, and then it downloads ANS and installs ANS, version 2.2. Then it installs Miniconda and installs Nylon and Python 3.6. If we wanted to run this, we would pipe this to Docker build -t. We'll give it a name, Eric's image dash. And what this will do, it'll say, I have 11 steps to complete. So it starts by pulling Ubuntu. So that's how he gets his Ubuntu Xenial version. And then it'll keep going along and installing every piece of software that you ask for. So that's how you can script now creating a machine. And once you guys get used to installing Docker and running it on your machines, which is possible now on everything, I know the Windows part still has variants depending on which version of the OS you have. You can build any of these machines by yourself by running these commands. Now, this does require getting used to Unix systems a little bit, but that world is where the richness of neuroscience tools are. And most things you use are in that space. So it's installed all the things, now it's downloading ANS. This will take a little bit of time.
Well, that's good.
Yeah.
A little bit about why Singularity exists and Docker can do all of this for us.
So I might have to give a little background to that question even. So many people here, you guys use your Windows machines, but there is a world of high performance computing that's your clusters at your universities and centers. And these high-performance computing centers, the way they typically work is you log into a machine and you submit jobs. It's almost never interactive, which is why those who do interactive things may not have ever heard of it, but that's how the large-scale batch processing. So when we talk about 10,000 images, you're not going to process 10,000 images on your laptop, or even on your desktop in a room. You may, it might take a month and a half, but on a cluster, it will take a day, depending on the size of the cluster. But that's the kind of thing that allows you to process things at high throughput, and why being able to program things on the command line or create tools to do so becomes very, very useful. So Docker came along and said you can generate these environments. And it provided this mechanism by which I can ship things to people which have exactly the things that I have, right? It's a binary set of layers that somebody else can take and recreate my environment. But Docker runs as root. The daemon, and root in Unix speak or system speak is giving a lot of privileges on the machine, which means a user running Docker could potentially hack the system. Now, in a typical cluster environment, that's not intentionally the case, but let's say they downloaded a Docker image whose intent was to hack the system. So now you've just opened up the surface area of an attack quite a bit. So most HPC centers said, we're not going to run Docker. There are a few which have allowed it, but they do it under images that they control. So they know exactly what's in the image that's running. So Singularity came along and said, we have a different way of doing what Docker cannot do. And it's another piece of software that's increasingly grown popular in clusters. And now, what we do is we generate Docker images, we put it up on Docker Hub, and on our cluster, we use Singularity to pull that image and run it. So now we have the best of both worlds in some sense. We can use Docker to replicate things on our local machines, local desktops, etc. And then on our cluster, we can take that same image, and it's as simple a command as Singularity pull Docker : / the name of the Docker image. And so Singularity now allows and many system administrators and HPC centers now allow Singularity, and it has a lot of good functionality for high performance computing. So in our center, we have Singularity running, and in fact, most of the time, we tell people who come asking for installing software, say, go use Singularity. You don't have to depend on the system administrators anymore to install software. All the system administrators need to do is install Singularity, and then everybody can run whatever software they want to run. And Singularity runs without escalation to root privileges, except in certain places, but that surface area is very well controlled. So that's Singularity. For those who are not in that world, that's a lot of Jabberwocky. So now it's gone on to installing Conda, and once that's done, it will install Nylearn and that's what it should say. So there are a couple of other tools like Neurodocker out there, which are general purpose packages which can generate virtual machines and Docker images. What Neurodocker really is focused on is providing neuroscience related packages as Docker images. So our intent is not to take over the world of package management for Docker. It's only the world of neuroscience related package management for Docker. Okay, so while this is installing, I'm going to go on to the next topic on that list, which is Reprozip. And for Reprozip, I'm going to just pull up an old lecture I gave. as an example. So whenever you run analysis, you would like to capture the details of your analysis. And you'd like to know how to do so, and how to use that captured information. So we're not going to run anything with this, just we're going to try to go through this pretty quickly. So again, the requirements, if you're going to use Reprozip, is that you need to understand the Unix shell. Everything we do, I think understanding the Unix shell is kind of a basic requirement. Docker and Docker image can be useful because Neurodocker actually supports Reprozip together with other Docker images that it generates. And it's in fact a nice way of capturing, but we'll go to the fundamentals of Reprozip. Okay, so why do we collect information? Well, to document and disseminate what was done, to repeat an analysis, to compare across analysis, and to understand sources of variance. And what types of information should you collect about an analysis? Well, your data, your parameters, your environment, your hardware, operating system, all the things we talked about earlier in the morning. Your code, your output, and your requirements. So when you hand off an analysis to somebody else, you have to tell them, these are my requirements. Requirements may say, yeah, I'm processing the Human Connectome project data. You may require a bit of disk space to download and run things on it. So those are the kinds of things that you want to convey. And there are a few tools. There's a typical tool on any Unix terminal called script. You turn script on, and every command you type gets logged to a file. And every output of it, it's as simple as that. You say script, creates a file, and then from then on, any command you type. It's a good old logging tool. And after you're done, you hit Control-D, and your file is there. So at the very least, if you're not using anything else, you should at least use script. Then there is Reprozip, and it's a Python tool that captures details of our, and Reprozip is super powerful in terms of the kinds of things it captures. And then there's another system tool called strace, but strace is not available across all Unix flavors. So on OS X, strace is replaced by dtrace, and you need to have super user privileges to run. On Linux systems, strace can run as a user. So there's a whole set of things that these tools support. We like Reprozip quite a bit. It supports a lot of these options that we're looking into in terms of capture. So I'm going to skip this thing because this is about how you get Reprozip running with Docker. On certain platforms, you require giving certain privileges. So otherwise, it's not going to run. And there are other things that are out there that you would want to think about when it comes to capturing information. Sumatra is a Python tool. Common Workflow Language is a specification to define workflows in a common way. It's slowly coming out. It's mostly in the bioinformatics crowd right now. We'll see there's some work going on in integration with Nipype and other tools. Nipype itself, which I'll talk about in a second, in a bit. And then Niceman is coming along. It's a way to create these execution environments. It's not quite ready yet. And AskInema is a tool that captures a command line video of anything you do. So if you want to show someone whatever you're doing on these Unix terminals, just like script, you can run AskInema, and it generates a file. You upload it to askinema.org, and somebody can see a video of all of your command line interactions. It's a pretty nice way of doing things. So for this, we had used script and Reprozip. And yeah, this is AskInema. So if I hit play, shows, it's a video of your command line. It's a really nice thing. I'm not going to play the whole thing over here because script, as useful as it is quite straightforward. You simply type script, you do anything you want to do, you hit Control-D, and then it's by default saves into a file called TypeScript. and you can see the contents of the file. Reprozip is the fun one. So it's being Python, you use pip or conda to install reprozip. And then you could do something like this. Let's see if I can do this bigger. No. I'll make this bigger. So reprozip has a function called trace. Give it a directory, and then you run whatever command you want to run. So it could be as simple as running vet, which is an FSL tool. It could be as complex as running recon all from FreeSurfer. And it will generate a config file in the directory that you point to. And we can take a look at the different sections in this file. So this file contains a version of reprozip, and it contains a section called runs, input outputs, packages, and other files. So what this does is it captures every single file that is used in any command that it's run. And you can take all those files, bundle it up, go to another machine, and recreate that environment in that machine. In fact, reprozip can create another Docker image with those files. So it's really a powerful way to capture all the pieces that were used in running things. So we can take a look at the different pieces of information that this captures. So here we have information about the architecture, things most of us don't think about when we're doing scientific things. But a lot of these things have impact on your output. As I mentioned, when we did this comparison between OS X and a Unix container, we saw a 10% difference in the values. And that's just architecture-dependent differences. That's not data-dependent differences. That could be a data/architecture interaction difference. But we don't think about it when we run things. We're used to our platform. Then we have inputs and output files. So it says what inputs were used. In this case, we were again using a Git Annex repo, so it knows what files we were using from there. And what files were, these are input files. And then it also, if you're using a Unix system, lists all the packages that would generate the files that you need to reproduce the environment. And so here we were using FSL core, and it lists all the files from that package that were used. So we can go through all these things that were used, but then here's the fun thing, which is you can give this pack command, and it packs all of it into this binary file. So after running this analysis, I have sent a 17 megabyte packed file that will allow me to repeat that exact set of steps on a different environment. So what we did, at least for this exercise, was we pulled a container that doesn't have FSL in it. And we ran this container, we installed reprounzip. So reprozip is the zip tool or the packing tool. Reprounzip is the unpacking tool. We use a version of the unzipping which uses something called shroot. And we unpack this environment. And so when we look at this environment, it has all the pieces that it picked up from our previous environment in here. And then it becomes as simple as calling shroot run better. And this repeats exactly the analysis that was run before. And while in the previous case, we didn't have this brain.nifty file here, because that was the output file. Once we ran it, the output file appeared. And one of the things we did was we did a diff between this file and the file that was generated. And there was no binary difference between these two files, which is what you want for repeatability of analysis. So knowing these tools allows ways of capturing things. Now, given what you've heard today, data lab plus reprozip, quite powerful. So you can version your analysis and pack it and distribute it together. So reprozip, Neurodocker, data lab, set of tools that would be nice for you to become familiar with to create these repeatable experiments. Okay, let's take a look at what happened over there. So there's an error. And the error is that nylearn is in conflict. Because conduct hasn't updated to the latest nylearn release things. So how do we fix this? We fix our specification. So instead of conda install nylearn, we would pip install nylearn. And one of the things, as I hit this, you will notice that it's going to skip all the steps that it has already done till it gets to the point where it has a new step. And redo just that step. So see, we're already at step 10 over here. And that's one of the nice things of Docker, because it uses these layers and none of those layers have changed. So it just rebuilds the layer that has changed. But it is sequential. The first layer it hits where it needs to change something, every layer will build after that. So it's a linear sequence of operations.
I have a quick question.
Yes?
Is there a tool for scanning your current Docker container and extracting a Docker file from it?
Yeah, Docker copy.
And then could we use an existing like Nipype container that has all these tools installed and then edit that Docker file to kind of do what this is doing, but
So you can't, so the existing containers don't have a Docker file,
yeah.
right? The existing containers has layers, and the moment you change it, you're adding a new layer, which basically tells Docker, remove these files and add these files.
Sure. So not using the copy command, is there a way to create a Docker file from a container?
As far as I know, no. Docker stores a lot of metadata, so it's possible that the line that created that layer is stored somewhere. And so maybe there is. I've never done that.
Yeah. I was just thinking because of this particular error, I wonder, you know, half these containers that exist that are put together and they're completely, you know, tested and things like that, and if it might be easier to then say, take that and remove the stuff from the working thing rather than trying to assemble.
It didn't like something. Why is it trying to compile? Nylearn requires GCC. I don't know why, but it looks like it.
Maybe default to a lower version of Python.
We can.
Yeah, 3.4.
So 3.5 would work because it said it was okay with 3.5. I'm actually surprised. It's possible they haven't updated their release. So there is a little bit of an iterative process when you run into issues that cannot be solved. So we're going to try and build up a constraint class in Neurodocker, which will try to infer this and tell you before you build it. But that gets to be really hard because that's like knowing every package dependency.
Yeah.
So far we'll just crowdsource this, which is you run into an error, you fix it yourself. Okay, so we've covered those three things. As you said, this is late. So the last two pieces that were remaining were showing you how to run Nipype or create a Nipype workflow, kind of the basic elements of Nipype. Let me first point out the Nipype tutorials because we are not going to cover all of Nipype, even if we were to spend an hour. These tutorials, just by themselves, take a fair bit of time to run. So at present, so I know you showed Michael's
Yes.
tutorial?
Yeah, Michael's tutorial.
So these are updated versions of Michael's tutorial. Hopefully all of them will get merged. But for the moment, I'm going to just pull up the latest versions of the tutorial. Yeah, the basic concept section, which is 16 different notebooks, is what would be essential for anybody to start writing Nipype code properly. Now you may skip some of them to get started, but that's essentially the requirements. Again, as before, they come with a Docker container. This latest iteration does require DataLab to download the dataset. We don't store the dataset in the Docker container. So things we've covered. And then you launch Jupyter, and you run through these notebooks as we've done for other things. So this has a lot of information, and you can always ask us questions on our chat channels and our Slack channels if you run into issues. But this is the full extensive Nipype introduction that one should go through if you're truly trying to learn how to do Nipype.
Satra,
Yeah.
please add the link to the
Docker.
sketch pack.
Yeah. What we were going to do very quickly today was to go through the hello world of Nipype. This is why I didn't use hello world earlier. I knew it was going to come up. We call it the quickest introduction to Nipype workflows. So for those who don't know the complete picture of Nipype, Nipype is a fairly simple package. Simple in the sense that it has only 3 components. A lot of effort has gone into this. It has a workflow engine, which is quite powerful, but it's fairly lightweight. And then it has support for all kinds of execution plugins. So if you're on, and this is a subset of things shown, so it basically supports any cluster environment. And you can run the same code locally on your computer, and you can move the code, just change the plugin, and it will submit things to your scheduler. So it is really quite powerful, and then as Tim has been developing for Porcupine, now you can generate a Docker image. So he's incorporating Neurodocker into Porcupine. So you create the Nipype workflow, it will give you a Docker file or a Docker generator command. So it creates the Neurodocker command for that workflow, and it will give you the Python script for the Nipype workflow. I think you'll still need a few things to tweak to make that Python script work, but you're basically getting both the environment needed for that script and the script itself to start doing things. So life will keep getting easier in some sense. But the general part about the workflow engine is it's a fairly lightweight but powerful engine. And so this quick introduction to Nipype really focuses on this workflow engine. I don't know if I can do this. So as with everything in Python, we import things. And this particular introduction does no imaging. It's all non-imaging. We write a simple function, returns the sum of a plus b. This is almost like our echo 1, 2, 3 example. We create a workflow, we call it hello. And this is the part which is syntactically important in Nipype, which is you create a node. So Nipype revolves around this idea of nodes. And these nodes have named inputs and named outputs. And then you're connecting things between these names of nodes. So the function interface in Nipype is a very powerful interface because it can wrap any Python function. So this Python function, so adding a plus b, could make a web call to a service called if this then that, and make your coffee. So you might say, run this workflow and insert a function that says, when you hit this point, use if this then that to send me an email, make my coffee, trigger my alarm, etc. So it's really, you can do almost anything Python can do to this function node. What's important is to tell the function node what the input names are and what your output name, because everything in Nipype is a named data flow. Right? And then you give it a name for this node, A plus B. You set inputs, because it's addition, it needs 2 inputs. You add the node to a workflow. You set the base directory, that's where it will use as its working directory. So the other aspect of Nipype is this concept of input source, input data, where your data comes from, your working directory, your cache, and an output. And the reason we have this cache is because Nipype remembers all the inputs, all the functions that have been used, whose inputs haven't changed, and it won't rewrite those. So if you delete your working directory, again, if computation is cheap for you, you delete the working directory. If storage is, or rather, let's put it this way, if storage is expensive for you, you delete the working directory. If storage is cheap for you, keep the working directory. And then you simply say workflow.run, and it runs this, and we can see that this particular node did its thing. If you give 1 and 3 as inputs, you expect 4 as an output. But I could change that function and just generate a random number if I wanted to as the output. Okay, so then we add another node. So that first workflow that we did just has one node. It doesn't do anything. Right? It just runs that one node. It doesn't do any data flow per se. So we add another function, and this function is very simple. It concatenates 2 things. Being Python, what those 2 things are, it doesn't care about. It just concatenates 2 things and returns a list of those 2 things. As before, we create a function node where we give this new function as input. We give it the parameters A and B, and we say, since it's returning a list, a descriptive output name called SumList. And now comes the other part, which is this connection. So what this is saying is, take that previous node, which we call the adder, connect it to this new node, which we call concatter, take the named output called sum from that previous node, and connect it to this named input called A. So that's how you create a link. And since this node requires another input, we set that input, inputs.b, go to 3, we run it. And if we check the results, we get 4 and 3, which is what we would expect with this simple workflow. Okay, so now we will try to add another node to this. We'll call it +1. It takes a single input and it adds 1. And as before, we define a new node for +1. This should now become repetitively similar for these function nodes. Input names, output names, function. And we create this connect statement which says, take the output of concatter, which we call SumList, and pass it to this input A of +1. And when we run this, Nipype says, oopsie, this node did not run. And one of the things Nipype has is a command line interface called Nipype CLI. And it's quite powerful, but among things that it does, when nodes crash, they generate crash files. And the Nipype CLI can display the contents of those crash files. It can also rerun those crash files. It allows you to debug it with Python. And if we look at the contents of this crash file, this is Python error, so you always have to scroll down all the way to the bottom of the error stack to understand what the actual error was. It says, can only concatenate list, not int to a list, because we were trying to add the integer 1 to an input that was a list. Python can't do that. Okay, so what the basic problem was is that this particular function cannot operate on lists. This particular function requires a single entity here on which this operation is possible. So Nipype has a construct called the map node. So we have been using nodes so far. And what map node does is basically says, whatever this field, iter field is, if I'm getting a list of objects over there, for each object on that list, I will apply this function. So adder looks like adder plus 1 becomes a map node. Looks exactly the same. The only thing that's changed is map node and the specification that I want that input to be treated as a list. We connect it, we run plus 1, and at this point, it does the right thing. It adds 1 to 4 and 3, so you get 5 and 4. So we've gone through a function interface. We've understood nodes and map nodes. So the difference between a node and a map node is that a node just runs on whatever sets of inputs it's given. If the underlying functionality, so if you're using something like FSL, FSL doesn't run on multiple items of things. Most of its commands are on single inputs. You would like to use map nodes to deal with FSL style things. The other concept is iterables. What iterables allow Nipype to do is you're effectively constructing a graphical operation. Iterables are like for loops on any parameter on any node of Nipype. So you can generate nested for loops just by adding that keyword iterables to various nodes. So in this particular case, I'm taking the adder node and saying that the input A is an iterable, and you should expect 2 inputs, 1 and 2. So let's take a look at what it does. Oh, this is a problem. This doesn't have the images in it. Give me 1 second. Okay, so we've taken adder, and we've created these iterables. We looked at outputs, that looks fine. We can also look at the graph that it created. Now, this is a fairly simple and straightforward graph. It's not a complex graph. If you look at Nipype's documentation, you can look at some complex workflows. So I will pull up the recon all workflow as an example. That's the recon all workflow. So one thing I would suggest is that robust operations often require a fair bit of complexity in the workflow. And so we shouldn't expect life to be always simple. Now, one can abstract out this complexity in certain situations, but to get the kind of performance that FreeSurfer provides over a wide range of data, they have a lot of elements that deal with the complexity or the variance of the data. Now we can talk this actually linked out to something, but maybe that's too slow. Yeah, and this is one of the reasons why graphical interfaces for creating workflows may often be not useful when it comes to complex workflows. Because not only do you need an interface, you need a good design element to that interface to make it easy to work with complex workflows. So simple things are often simple, and it can be done in both ways. When it comes to complex workflows like this, I often find that being able to script is an easier approach to doing this than having to do it graphically to link things. But that being said, one of the things I think we could look into at Porcupine is whether it can read these workflows back in. So right now Porcupine can generate workflows. It will be nice for it to be able to read workflows back in and allow you to edit some of the features of it. And that will be a nice test with these complex workflows to see how well the graphical design works out. So we have this, and what we can see now is that we had set this adder node with iterables set to 2, 1 and 2, and we can see that in the graph. We have 2 parallel pathways of the graph being executed. Right? So Nipype automatically took care of the fact that even though the inputs were set here, that's like running a for loop on the graph, so it created 2 copies of the subgraph and work with things. But the fun part about Nipype is you can set iterables anyway. So now I'm going to set iterables on another node of the graph. And when we do that, it not only creates 2 branches of the top level iterable, for the second node, it creates sub-branches. So that's like writing 2 for loops. You write an outer for loop and an inner for loop. Now imagine if you wanted to set iterables on multiple nodes in this, what your data management problem would be if you're writing a script. You would have to consider all these branching points and deal with it. All of that is taken care of under the hood with just specifying these iterables. And the final conceptual piece in terms of a workflow is if we have iterables which branch out, we must have some construct that takes things back in. And that's called a join node. And what a join node does is says, whatever you're iterating over, I can collect the information back in and reduce the space. So here we are simply adding a new function which will take this joined input and does some silly things. It just converts it to a NumPy array, multiplies by 1,000 and converts to a list. And this offers another thing about function nodes or functions. If you're importing a library, you have to import it inside the function rather than outside. Now if you're running a Python script on a local computer, this may not make much sense because you have all of these packages imported. But Nipype can send out jobs to remote computers. How does that job on computer N know that this package has been imported? So it's just getting this function. It has no idea of the global namespace of Python on that computer. So you tell that function explicitly, import these things. And so this is doing another silly operation, but it's basically saying, I'm going to add things. And the best way to look at the operation of this, so this is the simple graph, which is still a linear thing. But since we have set many different iterables and join nodes, this becomes a better representation of how you see what it's doing. So we still have 2 pathways for the top level iterable. We have a second pathway created inside each pathway for the concat level iterable. And here's where this join node comes in. It's basically taking these 2 things and joining it, and these 2 things and joining it. final thing in this hello world of Nipype is we've been running things just by calling workflow.run without specifying the plugin. We just specify a multi-prop plugin, which says use cores. And in this case, we're saying use 2 cores. So it will run things in parallel. So if you look at this workflow, these 2 things can run in parallel. These 4 can run in parallel. These 4 can run in parallel. These 2 can run in parallel. So you're not going to get a full 2x speed up because of something called Amdahl's law, but you're going to get quite a bit of speed up if you have cores available to do this. So just by changing the plugin, if you are on a computer that has multiple cores, you've sped up the process. You didn't need to write separate scripts that you call. This is automatically doing things. So let's map these concepts a little bit. So iterables, a good place to do iteration over in neuroimaging is subjects. So you're running often the same workflow on multiple subjects. That's a good place to set iterables. Map nodes, often if you're dealing with tools that don't support running the operation on multiple inputs, you use a map node. Actually, most tools in the neuroimaging space don't support running the same operation on multiple inputs. That makes tool development simpler. Something else should take care of it, which is what Nipype does. And then multiproc is one example of running in parallel. And so we're running it and we time it. This is a bad example to time because it says 355 milliseconds. It's really a silly, trivial workflow that takes 355 milliseconds. We can create a different base directory and run it. And it says 419, so it's the same ballpark. So we've just shifted the caching point to a different location called vault. But then we run it again by pointing to that same location. Something is wrong. It shouldn't take 364, it should be a few milliseconds. I'll have to check that. But what it should have done is said, I'm in the same working directory, I can pick up all the results, so I don't need to use time to run it. It's possible that what happened was I reran everything all over again, and even the first one picked up cache stuff because I didn't delete out the working directory for that. So those are essentially the key pieces of Nipype workflows. And this doesn't cover any of the interface stuff, which is where most of the effort has really gone in. So if you look at the documentation of Nipype, this column called interfaces is where the world of neuroimaging becomes available through Python. Because you can access almost every tool that's out there that has been used. And then on the left side, these examples and workflows. We call them examples and workflows, but some of them are things that we use in our work. They're quite detailed and sophisticated workflows at points in time. Just like the reconal workflow is embedded here. This is where the effort has gone in. So we can look at FSL, for example. And for everything in FSL, so every command that's wrapped around, you get a small example. Every input is described as what's mandatory and what's not. Most people come to Nipype's documentation to find out how to run command line tools elsewhere, because those command line tools don't tell this kind of detailed information as to what's mandatory and what's not. So, and that's why I say that's where the energy has gone into, because anybody who creates an interface has to understand it well enough to extract information that's not directly obvious from the interface itself. The way interfaces have been added is on the basis of somebody needed them. We don't go about taking tools and say we want to wrap every single command that's in the tool. That would be a nightmare, because something like FreeSurfer has 729 binaries, of which only a small 10% or so are used quite a bit. The rest are Bruce's personal development codes that are distributed. Some project needed it, it became a binary, it was distributed with FreeSurfer. So so if you're expecting to see everything, that's not there. But most of the things that are used quite routinely across packages are there. And one of the things that Nipype has spawned off are a set of libraries that sit on top of Nipype. So CPAC is not it is the conservative political action conference. Wow, it takes a while to get to. Oh no. All right. I will add another keyword. So CPAC is a graphical interface that's built on top of Nipype to deal with configurable pipelines for analysis of connectomes. A lot of it focuses on resting state data, but it can measure a lot of things out of these connectomes. So what CPAC does is allows you to generate dynamic workflows using Nipype as the base there. So that's one. I think I mentioned MindBoggle to a few folks. So MindBoggle is a software for morphometry or shape analysis of brains. And the MindBoggle routines or the MindBoggle container will run FreeSurfer and ANTs underneath, take that information, combine it, and extract surface-based information and shape-based information from those inputs. I think you've also heard of fMRI prep. And this is also built on top of Nipype, which is why when you look at this pre-processing pipeline details, you get to see all the different pieces of pre-processing pipelines. And they do look like Nipype graphs. But this is what's interesting, which is you can show this to someone, and Pierre was saying this, that you can show a graph instead of having a paragraph that describes the process. And it actually, I think, is intuitively easier to follow than trying to follow it from a method section. But as we've said, fMRI prep is a robust pipeline, and as with robust pipelines, they're slightly complex workflows. So you put all of these things together, and you get a nice workflow. So Nipype also has ways to subgraph things. So the fact that you see a box in blue, that's a sub-workflow that's contained there as a single node. And if you haven't used fMRI prep, you should if you're analyzing functional imaging data. It's a pretty nice workflow. And then the final one is MRI QC. So MRI QC runs a bunch of workflows for quality measures that it extracts from various images. Again, fMRI prep, MindBoggle, CPAC, MRI QC are all available as Docker containers. And especially for MRI QC and fMRI prep, if you have a BIDS data set, you just point to the data set and say, go run, and it'll extract the information for each one of them. So you can have the kind of chauffeur-driven cars out there, which will automatically run things for you, but you also have the full flexibility to go into it and make changes if you need to make changes. And finally, you'll run into many instances where you're writing little scripts or codes to do machine learning or other things. And that's where you could take the Nipype workflow constructs, and if you're doing cross-validation and you have access to a cluster, parallelizing things becomes very, very easy. So if you're doing permutation testing, the examples we had yesterday were trivial examples, but if you have complex models, they do take some amount of time to run. And so it's very easy to parallelize those things with things like Nipype. All right. So that's Nipype. And again, we are a pretty active group of people. You can ask questions if you run into issues with it. I would highly recommend going through the tutorials to understand the concepts better if you get into it. If you're going to run one of these pre-configured workflows, that's no different really from running a command line tool. You just point and you run. But if you ever want to create your own workflow for your own needs, so you may have needs that are not expressed by the interfaces at hand. You can use function nodes to add those needs into the picture. Let's see. Pretty much done. The last thing I'll leave you with is a paper we wrote recently, which sort of talks about this reproducibility angle. It's an F1000 research. It's called a very simple re-executable neuroimaging publication. Reference this, so there are a couple of nice things about this paper and the journal. So the way F1000 research works is you submit a publication, it comes online, and then reviewers review it. And all of the reviews are openly available. So you can read the comments of the previous rounds of reviews, as well as how we've addressed them. And I think that's really the way science should be. It's a really nice way to do things. What this paper did is it tackles a little bit about this generalizability problem, but the first step, which is repeatability. Can you repeat what analysis was done? And many things we talked about today are essential for this kind of thing. When we wrote this paper, we didn't have some of these tools that we did today. But yet, we have pieces over here that describe how you may repeat things. And I'll pull up the GitHub repo for a second to show you how some of this is implemented. But to start off with, the data are available as a Google spreadsheet. So it has a few things, and it has this file path over here which says where you will get the imaging data from. The workflow was a very simple workflow. What it does is it downloads the file, it reorients the brain, it extracts the brain, it segments the brain, parcellates the brain, extracts the volumetric statistics from each parcel, saves the results. So fairly straightforward and simple structural processing workflow. And then what we did was this was the result of reviewers' comments. So the first version did not have the Docker image. We were punting that for our second attempt, not at this paper, but this is kind of going to be a series of things that we work on. Increasingly complex things about database searches, queries, etc. Using provenance models and other things to annotate information. So, but a reviewer who wasn't a neuroimaging person said, I have no idea how to install FSL. You're asking me to repeat this analysis? How do I do that? So, so we created a Docker image, and he was able to download and rerun the analysis. And then the final piece of this is this Python check output.py. So we create a reference result that we store with the repository. And when you run the analysis, you can check if your run matched this output. And this is where the results kind of came out. Not to our big surprise, because we've seen this in many cases, that the reference run and the OSX run has a fair bit of difference. And these are percent average differences. So yeah, the right amygdala has about an 8% difference on average between two runs on two different platforms.
So it's kind of amazing because it's not a hardware bug, right? It's both Intel processors and
It's a library dependence bug. I shouldn't say a bug, but it's something that happens numerically different between these two platforms. So on OS X, we didn't run Docker. So whenever we run Docker, we get exactly the same results. So that's the repeatability of Docker. But what we wanted to show was that your environment matters. And so running on OS X, using the same versions of tools, gives different results. And so one has to be, and this also means that you shouldn't rely on single Docker environments for computational development. You should create multiple Docker environments that you test your tools in. Testing is really the crux of this, and where it boils down to.
I was just going to ask also, all of these things are very computationally intensive, and do you know for certain that the people running these and getting back the results were letting it alone, leaving the computer to sit and do all that, or were they also using it during that time? And does that not affect it?
I don't know the exact answer to it, but it should not, in principle, affect the way modern day computers work.
Okay.
Because there are different threads. There's no part of this process that relies on time as an element to say, I'm stuck, do something else.
Right.
So they're just threading threads that interleave with each other properly. So I've done things where I've run something in Docker, closed my computer, so it just suspended the process effectively, and then continued on when I opened it up again later on. So I don't expect that sort of, I don't think any of these tools, but I would have to go through the code or even create a test which loads up the rest of the system more to do things. On our cluster, for example, we get environments that nobody can touch
Yeah.
when we run things. So if we ask for 2 CPUs, we get 2 CPUs worth of computation cycles. So even if the rest of the load, so the load never exceeds the total number of cores that are on the machine. The load, the Unix load can, because of the number of threads waiting in queue, but the actual execution is only about interleaving those things. Yeah, so this, even with a simple example, shows that there's variability in your environment. And we, most of the time, just sweep this under the rug for most things. So this was our first attempt at doing so. And so the last piece I wanted to show was the GitHub repo itself, which is listed somewhere here. Okay, I'll get back to the GitHub repo, but I might as well start over here. So you've been using these Docker images. They come from somewhere. So Docker maintains a repo called Docker Hub, which is where these things have been coming from. So here is the simple workflow example. And you can see that our release, which was what's used in the paper, is from 3 months back. But this latest image is only 14 days ago. And why is that the case? Let's go take a look at the repo. So it's a GitHub repo, so we can go to GitHub. And I merged somebody's pull request 14 days back. What that does in this repo is it triggers a test cycle that's run, in this particular case, on a resource called Circle. So Circle is a continuous integration platform that can automatically run tests when changes are pushed to your GitHub. And when it does that, it returns whether that test passed or failed. And the way we work in most of our software development enterprises is that we don't merge things into the main branch if our integration test fails. And that's how you keep increasing how software works in robust ways. because you don't want to integrate a patch into your software that actually doesn't pass all the tests. Do we have complete coverage of tests? No. But this is at least a starting point. And in fact, this test that we do in Circle is a limited test. So in the paper, we ran 24 participants worth of data, and that takes a little bit of time to run. For the Circle, we just run the first 2 participants worth of data. So it's a quick sanity check that you're still getting the same results whenever people are storing things in. And if you didn't like my fascination for Docker a whole lot, there's more fascination for Docker. We actually use Docker to run tests inside Circle online. So that's how we keep the environment intact, even when Circle is changing its environment and running things. But this demo itself, you can execute with Docker. You can execute in your current environment. So if you have FSL, curl, git, or unzip installed on your system, you can run this command, which is a single script, and it will run the demo for you. You can build another Docker image with a different custom environment. Neurodocker didn't exist when we submitted this. We would probably, in the next version, update this to using Neurodocker to build a custom environment. But this is kind of what prompted us to start working on Neurodocker. It's like, we want to test multiple environments. There is no packaging manager which does that right now. And then the final bit is, if you have Singularity, you can run this using Singularity itself. So there are many different ways in which you can run this repeatable experiment, and you should get back the same result. And what does running mean? It involves 2 Nipype workflows. The run demo workflow, which runs the actual workflow, and then check output.py, which checks that the output that you got matches with the expected output from this data set. And this doesn't take much work to do. And once you get into the habit of doing this for your own work, you'll find that it will either raise flags for you yourself in certain cases, or that it'll give you a very nice feeling that your results are not changing as you change different environments and other things. So it doesn't take much to set these things up. And that's why I mentioned the Unix one, because I heard many people are not familiar with Unix, so that's one thing to learn. 2, Git and GitHub. Because as you can see, I'm not doing half of this work manually. I just set up things and the machines take over. Yes, which might be a scary thought, but at some level, it's quite automated. So anytime I make a change to the code, it will rerun things. And I can click on this green button and it will take me to Circle, who will tell me all the times that it ran the code. And we can see that there were a couple of failures. That wasn't good, which led us to fixing things. So it's really a nice way of checking consistency of output as your code or environment now changes. Because now we can create Docker files on the fly. We can augment, so the next version of Simple Workflow, which will also be called Simple Workflow, version 2, will now test these different environments on the fly as well. So we'll get a matrix of output as to the different environments automatically. And that's what we're trying to get to with a couple of these projects, is to create a visual representation of variability in software. So given the same data, do your various software environments, how much variability does that contribute? If it doesn't, fantastic. But if it does, we want to know.